Okay, thank you very much for having me here. I'm really happy to be here at Cargèse. So, well, Jan was supposed to come, but I'm here for as a replacement, but I'm still happy to be here. So today we'll talk to you about other aspect about distributed acoustic sensing in the context of monitoring earthquakes with submarine cables. This is not only my work, so I've been working with a lot of collaborators such as Diane, Martin, Clara, Marie, Claudio, and Eugene. And so basically, why are we so excited about using DAS for instrumenting the oceans? Well, mainly because instrumenting the ocean is pretty difficult. The ocean bottom is hard to access. And in seismology, we developed some strategies such as OBSs, mermaids, which are nice solutions, but which are temporary solutions. You only recover the data generally 1 year after, except for mermaids, which has this capability to go to the surface to transmit a major event when they occur. And so for making a permanent underwater observatories, this is not a real long-term solution, let's say. So the best way to go is basically to use those cable solution. And here it's an emblematic example, which is the SNet network in Japan. But keep in mind that those solutions are very, very costly. We're talking about $500 million for SNets. And also, all the solutions are quite expensive. And this is why where DAS come into play. Because with DAS, we can use this amazing network of submarine telecommunication network and basically plug our instrument into it and take into advantage that those cables crisscross the oceans, sometimes in an area of great interest in terms of seismology, and particularly in subduction zones. So, for example, the Chilean margin that I will show you right now. So this is in this context that Diane Rivet set up this ABRIS project, which goal is to install some kind of prototype of ocean bottom DAS observatory. So basically, we went there, we put 3 instruments that will stay there for 5 years. And basically, we went there in last October, so it's quite new. And I would like also to stress out how easy it was to set up this installation. Basically, we went on those server rooms, and in 2 days, the thing was set up. So 2 days for 450 kilometers of coverage was a pretty good score, I think. So what are the challenges of such projects? Basically, what we want to do is to take advantage of the proximity of the cable to the core of the action in the subduction context. And what we want to do is to try to detect small signals that are difficult to detect from on-land stations. We want to image this part of the crust, which is also poorly covered by instruments, monitor its change, and also eventually develop maybe prototypes of offshore early warning system, because we are closer to where big earthquake occurs, so we can send alerts earlier. Okay, this is the context. And here we thought that DAS is really great in terms of getting access to remote area. But there is a second aspect which is also really great about DAS. It's provides some kind of a new measurement paradigm by providing continuous recording along space. So here I'll show you an earthquake that we recorded with one of the cables. And from this far view, let's say, of our wave field, we can clearly see the P and S onsets. But the nice thing is that we can go actually through the scales, we can zoom in. And already here we can look at the waveform and see that, well, it's not that smooth anymore, it's pretty distorted. And we can keep zooming in. And basically, if you really look closely, there is a lot of information here. It's super structured, very sharp features. And basically, what we can think a little bit about it is that you expect a small structure in the wave field to correspond to close by heterogeneities of the Earth. Something which is far would produce spherical waves, so we expect to have something which is smooth. Here, we are looking at really strong heterogeneities, which are probably very shallow. And this is the second thing I think which is nice with DAS. It really forces you to look at the fact that the Earth is heterogeneous, and you need to take into account this aspect if you really want to go through, do a good imagery, let's say. Okay, those were the adventures, and one big challenge of DAS is to also this question: what about the instrumental response? And a lot of people have been studying it. So I think we'll talk about it because that's measure strain, whereas we're used to work with displacement. So this is a really quick overview of this talk. I will go from small scales, look a little bit to the structure of this waste field, and then take a step back to look at the move out of the those arrivals to do classic seismology, so locate earthquakes and things like that. And we'll talk briefly about early warning at the end. So I would like to start with this really small and simple, small deployment we made in Italy a few years ago, where the idea was to have this L-shaped array and do, for example, beamforming, so let's say array processing techniques with it. But it didn't happen exactly as we wanted. So on the left, you can see 2 earthquakes we recorded. And what we wanted to see is what we're expecting to see is basically, so in red, I put it the theoretical arrivals. And we're expecting to see 2 waves, basically there and there. But in the end, what we see is much more complex. What we see is like, we still have 2 arrivals, but the waves that we see are very slow waves. And if you look at the slope, we are talking about 60 meters per second, 130 meters per second. So we really don't follow what we're expecting. What we can see is that there is some pattern that is repeating. So from the P to the S arrival, the pattern repeats, but also from an event to another, we always have these same patterns. And basically, this pattern is the signature of the subsurface, which at that small scale, so on a 1 kilometer cable, is the dominant effects that we see on DAS. So we can actually explain this a little bit with the theory. And the thing is that if you look at how it's strain compared to displacement, basically one is a derivative to the other, and you have this GK factor, which is additional factor, which explains that basically DAS, like a strain measurement, is much more sensitive to small and slow waves. And this is not very good for us. So actually on that particular site, because it's online, we could do some active tests, characterize how waves were traveling inside of it. And what we have seen is that what we mainly record are those waves that enter from the tip of the basins and travel horizontally in the layers of the sediments, which is not good because what we would like to see is a direct wave, which is less distorted and less, so we can better use to characterize our sources. So let's say that from that point of view, we can say that strain is worse than displacement for seismologists, let's say. So is it the end of the story? No. So what can we do if strain is worse than displacement? Well, a really naive solution is say, okay, could we go from strain and try to retrieve displacement? And actually, it's not that difficult. So because the one is a derivative to the other, basically the other is the integral of the first. So if you integrate strain, you basically get displacement plus some constant term, which is a little bit annoying, basically because you're missing this integration constant. So you need to find some trick to remove this constant offset you have in when you integrate. And to do that, what you need to do is do mean removal. I won't talk too much about it, but you need to remove actually the very low wavelengths, which can be artificial. So there is a small limitation here. Yet, if you apply it to real data sets, so here we are in Stromboli, a very heterogeneous area, a volcano, and we have a small deployment, so with a linear segment of about 100 meters. And what we can see is that, so we put a node in the middle of each section, and what you can see is that if you apply this method, you can retrieve very good agreement between, so in black what the nodes records, and in red what we recovered using only DAS and nothing else. So from this we can say that, okay, a DAS deployment can be used basically as a really some one component array in the direction of the cable that measure displacement or velocity or acceleration. So let's go back to our initial problem. Does it improve what we see? So this is another earthquake we recorded on one of our cable in Chile. On top you have the raw recordings, and on the bottom the ones that were converted. And you can see that indeed it clears pretty much the recordings, both because it improved a little bit the signal-to-noise ratio, but it enhanced especially those highly spatially coherent waves that we were difficult to see at the beginning. And actually, you can interpret here those waves. So we have 3 arrivals, and instead of 2, like only P and S. And this second wave here, yeah, it's actually, maybe on the next slide, it's actually what we're observing here is a splitting. So as the sediment and bedrock interface. So we are underwater, and in the ocean, most of the ocean are covered by quite thick sediments. And those are quite annoying because sediments have very low velocities, high VP to VS ratios, so they distort very much our wave fields. Yeah. Yeah, and I discovered that basically here in Cargèse, we can say that they act as an aberration layer for Alexander. Next slide now. Okay. So we wanted to try to characterize this aberration, this effect of the sedimentary layer on our recordings. And we went back to really old methods. Basically, we picked manually those events where we can see the splitting. So we draw a line on the image and try to see if we could find the recurrent characteristics. And indeed, if you do that for, we did for 30 events. And the first thing we started to look at is this time difference between those 2 waves, so the direct and converted wave. And this information, so we did it channel per channel for the 30 events. This is the mean and the variability. And that you can see that basically the effects of sediment are pretty constant. And this was quite expected because we have really low velocity in the sediments. Well, the waves enter the sediments, they almost go vertically when they are in the sediment. So it doesn't really matter where the event is located at the beginning. So basically it means that you can use this kind of measured delay as correction terms. And also you can infer some really simple modeling of your sedimentary layer, because basically the delay here is proportional to the thickness of the sediment. If you suppose that the average velocity of the sediment is pretty constant in the region of interest. Yes? So, yeah, well, this, what I call PP here, could be actually the direct P you're talking about. It's the P wave that stays as a P wave in the sediments. Yeah, that's the direct P, yeah. Yeah, and so once you have a first order modeling of the sediments, you can do things like improving your localization methods. So here I show you what happens if you don't do any correction. So in black you have the theoretical arrival from the regional model. In red are the picking of one events. As you can see, we don't model the converted arrival because in those regional model you don't have any modeling of those. And if you use this first order modeling, you can much better fit the arrivals, have also a model for the converted one. And in the loss landscapes, it's improved things. So we also want to point out the second problem we have with DAS is the fact that usually when you use a telecom communication cable, well, those cables go from point A to point B, so they're usually quite a straight line. And this for localization is pretty bad, because basically this cable axis works as an axial symmetry, and you have a strong ambiguity in your localizations. I will talk a bit, go back to this a little bit at the end also. And there is a second example which I find quite exciting. It's the work of actually our colleague Wu-Jing Xie. She tried to do back projection, some kind of beamforming with this DAS cable. And what she showed is that basically, because DAS recording, if you do the raw signals, you mainly have scatterings and things like that. Usually the beamforming is not stable. But if you apply both this conversion to displacement, so you filter a little bit the scattering, and you apply this correction, then you can finally get some focusing of your beamforming, which otherwise would be impossible. So this was a pretty good result for us. Yes? So you basically take your 2D image and you do cumulative sum along the spatial axis. So it's like a cumulative, so it's, yeah. No, no. Just it goes through the signal, and then for removing the average, we do like sliding window average, and we remove that part of the signal to remove this the fact that the signal tend to diverge away when you do the integration. Okay, so this is already good, but we're also working to try to improve this modeling of the sediments. And this is work of Clara Vernet, which is a PhD student. She's trying to do a kind of joint inversion of the sediment, both using FK analysis. So basically, she's fitting dispersion curves to get the gradient of velocity in the sediments, and she used this delta T to help the inversion to constrain the thickness of the sediments, basically. Okay, so yeah, any question on this or yes? Yeah. Well, I'm not really an expert on this, but I think maybe this image maybe give you some like this seismic profile. So I think we have quite a strong impedance contrast here. Yep. Yes. Yes. I will get to this after. Yes. Okay. Where the dust is? That's a good question. So yeah, really good question. Actually, we know it to some extent. So we had basically when the ship installs the cable, they mark where they are passing. So, but still you have some uncertainty because the position of the ship is not exactly the position of the cable. But there is a second and quite more important source of error is that basically you have the geometry that they give you, but then you need to know when you send your lights through the cable where it goes back. Well, so you need to fit, let's say, the optical distance with this geometrical distance, and they don't necessarily fit. And for now, we don't have strong constraint. And so Jan is actually working on using ship noise to try to, because we know where ships are, and so by basically trying to locate the ship, you can do the inverse, try to retrieve where the cable is. Okay, let's go ahead. Come on, okay. Okay, so so now we can go to this second part, which is basically, okay, we have characterized the sediments. We are not really using it right now for improving the localization, but yet I will show you some stuff about locating earthquakes with DAS. So basically what I showed you in the first part is that we can convert each trace of the DAS to velocity. And velocity is what basically a seismometer would have recorded. So from that, basically we can reuse all the classical chain of tools to locate earthquakes. So the only new thing is that we convert to velocity at the beginning. We apply a little bit of spatial sampling because, well, 1 point every 10 meters is not really useful at that level. And then we can apply usual peak, also PhaseNet. PhaseNet work great on velocity converted traces, association, localization. And for magnitude estimation, we can... Yes, so, yeah, so those points are in black, like all those black and grayish peaks are basically raw peaks from PhaseNet. So there is a lot of superuse peaks, especially at that scale when you look quite far. But so this is what actually then gamma takes as inputs to do the association and to basically isolate groups of dense peaks that are events to those kind of scattered peaks, which are probably nothing. Yep. And for local magnitude, you can either use local magnitudes with usual scales, but actually one of our collaborators, so Claudio Strumia, which is also a PhD student, developed the theory of the Bruin source and everything directly from strain, and it shows that we could actually directly fit Bruin spectra on on dust traces. So you need to integrate through time, not in space. And then he showed that basically we can retrieve things like moment magnitude, corner frequencies and stress drop values. So, but this is like classical seismology. You just need to change a little bit the theory. And yeah, here's what we get from this all analysis. So on that plot, we have one catalog that actually Marie Baillet, which is one of our engineers, did. So you have 3 colors of point of that plot. It's maybe a little bit blurry, I'm sorry. But you have, so the yellow dots are DAS-only located events. The white dots are events that are located from the inland stations. And the blue dots are events that we located using actually both networks. When we had detection on both, on both networks. And I think the main message here is that basically DAS allows to really increase the number of detection in a radius which is about 50 kilometers around the cable. But the problem is that for now, those events, we cannot locate them very accurately because of this ambiguity. So our, let's say, strategy for the future is when we went installing the DAS, we also installed a temporary station to densify the network, which is pretty sparse in the area. And the strategy will be to, we don't have the data yet, but the strategy will be to basically using combination both network to locate, let's say, master events that we can locate accurately, and then try to relocate all the other events that are only detected with DAS relative to those events. So basically, the strategy is to try to learn a little bit the complexity of how wave propagates in this area with the temporary station, and then use this information to locate the other events afterward. Okay, a little bit about, so maybe any questions on that part before I start with early warning? No? Okay, good. So what about early warning? So Lior et al. And Jan and all the colleagues estimated basically how much time can we gain from having instrumentation in the ocean bottom. So this is a map where we can see basically the gain in time in terms of sending an alert, depending on where the earthquake occurs. And according to this map, basically for several depending on where the event is, you can win from 0 to up to almost 25 seconds. So this is a great opportunity to try to set up new strategies to get alerts sooner. But one of the main issues we're encountering now, and Zhongwen talked to it a little bit this morning, is the saturation issue of the DAS. So this is a magnitude 6.6 event that we recorded with the 3 cables quite recently. And so the event occurred actually just below the end of the 3rd cable. And we can see that basically the signal is completely destroyed, it's completely saturated on almost 300 or maybe 400 kilometers. So basically we don't get much we can still get the first arrival time. We kind of see the S arrival sometimes, but the signal is really distorted, and especially if you want to estimate the magnitude, this is really not good. So Martijn van den Enden worked a little bit on the subject, and he worked on characterizing actually when DAS saturates. So he actually the equation that dictates when DAS saturates is pretty simple, and it takes into account actually two important parameters, which are these sampling rates that you use at the beginning, and also the spatial and temporal sampling rates. Basically, the faster you sample, the better you can unwrap the phase, and so the higher is the dynamic range of the instruments. It's important to notice that those are like the sampling that you set up at the acquisition. Then if you want to do decimation to reduce your data, this won't affect the dynamic range. So it's important to basically set up your instrument at maximum, then you can do decimation. And one thing that limits the maximum sampling range that you can use is basically how much time it takes for the light to go back and forth in the cable. So there is a little trade-off between sampling rate and how much of the cable you want to sample. And you can translate this in actually magnitude, distance limits. So in black, here it's the limit we had when we first started. Since then we changed the parameterization, so you're more like here. But basically, at a few tens of kilometers, we start to saturate at magnitude 5 right now, which is really not high. Yet there is still some hope, because Martin is working on several ideas. The first idea he's working on is basically to try to look at degree of saturation, because your signal don't completely saturate, it's progressively saturating. And so you can look at the statistics of the signal to try to estimate this, and then go back to, let's say, an amplitude factor above the dynamic range. And from this, basically showed that there is a progressive saturation up to a factor 10. So there is a factor 10 we can get there. There also factor 10 we can probably get from better unwrapping strategies. And also another factor 10 we can use by actually using cable part of the cable which is poorly coupled. So those are part of the cable that usually though you don't want to use because they don't record well the seismic phases. But in this particular case, this is what we want, to have sections which are not sensitive to the waves, so they don't saturate. Okay, actually I went faster than I thought. So I will finish on a little slide about toolbox we are developing. Yeah, sure. So what frequency do we saturate? Yes, yes. Lower. Yes, so I think what Martin showed is that the lower, the easier it is to reconstruct the signal, because basically maybe we can see it, for example, so here what we have is a swell. So it's it's recorded very close to the shore, and it's a very low frequency signal. And so you can clearly see when the signal is jumping because of wrapping, which means that, yeah, in this case, it will be easy to reconstruct, for example, the signal. Yeah, other questions? So yeah, we are developing this little toolbox to treat DAS data. So feel free to use it if you want. Basically, the main idea is to try to deal with the fact that it's complicated to work on data sets that don't fit in your computer's memory. And yeah, I could improvise some stuff, but I think it's better to stop here. So some take-home messages. Basically, you can use DAS as a permanent underwater observatory, because also we know how to convert stresses to displacement, which, as I shown, is better than strain. So really, this can be the standard seismology tools. We've seen that actually the sediments act as some kind of barrier to find observation what is happening below, but we are starting to have strategies to characterize the sediments to improve it. And well, in terms of early warnings, we are still quite limited by saturation, but we are working on other way to improve it, and probably we could go up to magnitude 7. But to go further, I think we need to think about other instrumental strategies, maybe complementary instruments, because DAS can give you the localization, and then if you have a few stations that, for example, give you the magnitudes, then you're good to go, let's say. Yeah, and I think that's all for me. Thank you.